Okay, so on the far right-hand side of our line, we're putting radio. On the far left-hand side, we're putting gamma. So radio waves and gamma waves. Next to radio, we're going to put microwave. And this is all relative. I'm not drawing this to scale by any means. To the left of that, we're going to put infrared. IR is what this is called. And then we have the visible light spectrum. And the order that I am doing it in is actually opposite of what you probably learned. It's Viv G Yor. If you heard it as Roy G Biv, the colors of the rainbow, same thing. I'm just doing it in reverse, okay? Then to the left of that, we have ultraviolet, which we call UV. And then to the left of that, we have X-ray. So your spectrum should look something like this. This spectrum can actually be about three different things. It can be about wavelength, it can be about frequency, and it can be about energy. It tells us all three of those things. So I'm going to go through all three of those, but we're going to start with wavelength, okay? Waves. Imagine a jump rope or just a rope, a battle rope, if you're familiar with a battle rope. Imagine taking a rope and doing this with it. If you do this, if you have a battle rope and you're doing this to it, what's it going to do? Is it going to do that? It's going to snake, okay? All right, so that's the wave I'm talking about, okay? That's the easiest one to discuss with this. This is not a physics class, this is a chemistry class. If you've had physics and you probably had this in the physics class, they went into a whole lot more detail than I'm going into, okay? Just to warn you. But what we're dealing with here is waves. So I'm dealing with this kind of wave today. That's what I'm talking about. Wavelength, I'm going to give you an example of wavelength. Every time, and wavelength and frequency, it's hard to discuss one without the other. So let me talk about both. Waves are measured in their length by either peak to peak or valley to valley. So we measure a wavelength by their peak to peak or their valley to valley. And frequency is how often that wave passes a certain point. So if this right here is my point, this is my point, and I'm measuring both, I'm going to give you a demonstration of both wavelength and frequency with this demonstration, okay? So every time you hear the clap, that's when the wave passes that certain point, which is also an indication of the wavelength, okay? So I'm going to make you a noise for a minute. So that's one wavelength, okay? That's one wavelength. Now this is another one. Which wave was longer? The first one. Which wave was shorter? The second one. Which one had a higher frequency? The shorter wavelength. Does that make sense? Pretty easy to understand when you see it like that. And so let's look then at what that means. Those radio waves are the long waves. That's a long wavelength. So radio waves are long wavelengths. So I'm just going to put long waves. And they had what frequency? High or low? Low frequency. Gamma rays over here are short waves. And they had what? high frequency. So long wavelengths don't pass a certain point very often because they're long. That should make sense, which is why they have low frequency. That would be why they have low frequency. Short wavelengths pass that certain point more often, which is why they would have high frequency. Now, before I leave this, some of you perhaps have heard of shortwave radios. Have any of you ever heard of a shortwave radio? Yes, no? Ham radio operators, you may have heard of them as, anybody a ham radio operator? You may know anybody that's a ham radio operator? I don't know of anybody either, but I know that you sometimes, not very often, but sometimes you'll see on the on a license plate or something, it'll say something about their ham operator or something like that. I can't remember exactly what it says, but I've seen that. It's actually a very useful tool. When other radio frequencies are bombarded, you can actually go onto the shortwave radio and transmit information. It used to be used a lot more than it is now, I think. Where would shortwave radios be? They would still be radio waves. They would just be closer to what? Closer to microwaves. They're still going to be on that end. But they're going to just be shorter than normal radio waves. That's just what that would mean, okay? All right. Now, I said that this demonstrated three things. It demonstrates wavelength, which we've identified. It identifies frequency, and it identifies energy. Now, based on what I've already done, which of these has the highest energy? Gamma rays. Gamma rays. Where did you feel more energetic with my demonstration? The fast one, didn't you? Didn't that one make you just kind of irritated? But you definitely were more energetic, right? Does that make sense? So those faster wavelengths, those shorter wavelengths, I should say fast, those shorter wavelengths which were higher frequency are greater energy. They have higher energy. So a short wavelength will have higher energy. A long wavelength is going to have lower energy. It's going to have lower energy. Now, I will show you this in a pretty picture, but I wanted to draw it because if I hadn't have drawn it, you wouldn't have written it. So here is a pretty picture, and that's what I was talking about as far as the waves up there. But here's a nice pretty picture. I even wrote nicely on this one. And that actually shows you a little bit more about wavelength. And it's a little more to scale, definitely, than mine was. And so you can kind of see, I was not to scale, and I told you that to begin with. I was not to scale. But I wanted you to see this for the colors because I think you all understood what I meant, but I wanted you to see the rainbow colors. That's what we see when we see a rainbow. So where's this going? Well, that visible light spectrum has, what is a spectrum? You know what's funny? When I was a student 20 years ago, 30 years ago for sure, the word spectrum was not something I heard spectrum from electromagnetic spectrum. That's where I heard spectrum. But that is not, we hear spectrum all the time now. It'll be all kinds of words used, or all kinds of phrases, or all kinds of situations. Something will be said about a spectrum. It's a spectrum, or on the spectrum, or whatever. And so here, this makes more sense probably to you all than it did to me, because it is a spectrum. Something I think of when I think of spectrum is relative. It's relative to each other. They're all relative to each other. The same is true on this entire spectrum as is true in the visible light spectrum. So that means red light, tell me about it, compared to green light. Anything based on what you see here. Lucas?
Oh, it has a
red light
does have a lower energy than.
That's exactly right. Red light would have a lower energy than green energy. Would red light have a longer wavelength than green energy?
Yep.
So what is the highest energy color?
Violet.
Violet. Violet is the highest energy color. Now, How do I remember this? I remember this strictly based upon, does it hurt me or not? If something hurts me, that indicates it's probably high energy. Would that make sense to you? If it hurts you, it's high energy. As much as I think I'll look much better with a good tan, ultraviolet light, what to me? Hurts me, really. Ultraviolet light is damaging my skin. So ultraviolet light is higher energy than is infrared. Does that make sense? Radio waves obviously are all around us. Are they hurting us? Not that we know of, or we'd all be hurt, right? But gamma rays, you may know what gamma rays can be used for? You may know what gamma rays are used for? They can be used for isolated cancer treatment, correct. So are they killing? Yes, they're definitely killing. X-rays, are X-rays going to hurt you? Generally speaking, in a low amount of X-rays, a little bit, couple times a year, maybe one, or probably not even a couple times a year. You know, I had a lot of X-rays when I was a little girl because I was always doing something wrong, fell or something. So I had a lot of X-rays. But what do they always do when you're having X-rays? They put a lead apron over your main body. So I had a broken leg as a little girl, and so they would always put this lead apron over my whole body and then just X-ray my leg. When you get your teeth X-rayed, what do they do again? Put a lead apron all over you. And does the person doing the X-ray stay in the room? No, they go out of the room. They go out of the room. So that tells you those X-rays are damaging. They're damaging. They can be, okay? And like we already said, ultraviolet, it's less damaging than X-rays and gamma rays, but it still is not good for me. So that means if it hurts me, it's high energy. Ultraviolet's near violet. Is that an easy way to remember it? Infrared doesn't hurt me, and it's near red. So if it hurts me, it's high energy, short wavelength, what? High frequency. High energy, high frequency, short wavelength. So hopefully you can remember it that way. Now, that is like, okay, deal, that's interesting, but what in the world does that have to do with anything that we're talking about today? Well, up until this point, I have talked about protons, neutrons, and electrons. And who plays the part in forming compounds? I've told you that. Does anybody remember that? Which of those subatomic particles plays the role in forming compounds? Electrons. Electrons play the role in forming compounds. That's who plays the main important role in forming compounds. So what electromagnetic spectrum helps us understand, along with everything else we're going to talk about, is basically electrons. And that's what I already told you today. We're going to learn where the electrons are. By the end of today, hopefully you're going to start to realize, oh, that's why those ions have the charges they have. That's really why I teach this, is so that you get the better view of ions, and it makes more sense to you. Fireworks. That's my next comment on here, fireworks. So what do fireworks have to do with this? Well, give me anything that you saw in that picture even that would help you think about why fireworks might have something to do with this. What was in the middle? What's in the middle of this? Color. Color. What do fireworks have? I know most of you are thinking booms and bangs and firecrackers, but we're talking color. I'm talking color right now. I'm talking color. So, fireworks. Did I put online for you all the fireworks article? Did I put that in your notes? Okay, I didn't think so. I put that in my 109 notes, and I didn't think I did. There was an article that I found, and it's so old now, I mean, you all would crack up. It's actually a 2020 article, not a 2020, a 2000 article, a 2000 article, which cracks me up because it's before you all were born. But I remember exactly where I was when I printed that out, and internet was fairly new back then. But it was an internet article on fireworks and how fireworks work. And I thought that's why it says fireworks article, but that's okay. If we don't have it, that's okay. So let's go to what we know already, and then I can basically tell you what the fireworks article said. So you know that electrons exist where? I've mentioned this in past conversations. The outer, what do we call this? The electron cloud. And some of you have had chemistry before, but I think I've said they exist in the electron cloud, and if I didn't, that's okay. But earlier, typically, what I usually say is protons are where in the atom? Protons are in the nucleus, and where are electrons? In the electron cloud or outside the nucleus. That's what we'll say, outside the nucleus. So not in the nucleus, they're outside the nucleus. So, what's going on? Why do we see colors in fireworks? Why did you see colors in your flame test the other day? You going to answer it? It's not just heat. It's literally the fire. It's not just heat. It's fire or electricity. So what happens? Let's talk about a basic atom. Typically, and some of you are getting close. Some of you are like really leaning down in your chair right now. You're kind of like laid back like this. You're getting to your ground state, what I would call your ground state. Ground state is really when you're asleep. That's your ground state. When you're lying down and you're asleep and resting, that would be your ground state. That's your resting state for you. I'm going to write all this down in a minute. Just listen to me right now. That would be your ground state. Well, for an atom, the ground state is when their electrons are in their lowest energy levels possible. So we're going to go into what all those energy levels are in a minute, but I'm going to just give you a big picture of it. So the nucleus, and you're going to see me do my body up here a lot. The nucleus is kind of like my belly button, okay? So here's the nucleus, and then outside the nucleus are these energy levels. If I had a visual for you to use, if you're not seeing this, this is what I see when I do this lecture. I picture a series of hula hoops. You with me? Picture a bunch of different size hula hoops that are around me. Okay? That's what I'm picturing. And so the nucleus of the atom has what charge?
Protons and neutrons?
What charge? Positive. The charge is positive. Yes, it contains, Katie Good, protons and neutrons. That's what's in it. Protons and neutrons are here. All the mass is here, but what's the charge? Positive. What is outside the nucleus? Negative. Okay? These energy levels are what these are called. These hula hoops I'm talking about, those are energy levels. And so we have electrons that are in these energy levels, and they are certain distances from the nucleus. Do you think it would take much energy to exist in the first energy level? Now think, I want you to think. What charge are electrons? What charge are protons? Would it take much energy to exist in the first energy level? No. Why not? Forget neutrons. Protons are what charge? Positive. What charge are electrons? Electrons. Negative. What do positive and negative do to each other? Attract. They attract, don't they? Think of magnets. Do positive and negatives attract? So positive nucleus is holding on to these negative electrons, and are they close to it? Yeah, it doesn't take much energy to do that. It doesn't take much energy to do that because you're right here close to the nucleus. As you go farther from the nucleus, however, would it take more energy to be in this space out here? It has to maintain being here because think of magnets. Have you played with magnets? Think of magnets. If you haven't played with magnets, find some magnets and play with them. Take an old pair of headphones apart and find the magnets, and those are some really cool magnets. Play with them. Okay? And you're going to find when those magnets if they're good magnets, any magnet really, if it gets so close to each other, it's tracked together. If the sides are opposite. But what if the sides are the same? What if you have the polarity is the same? What's going to happen when you get it close? It's going to push it away. It's going to push it away. Well, in order to be out here, it takes more energy because the positive-negative attraction is not as great. So what we find in fireworks that actually happens, and how we know what we know about energy levels, is there was a person named Niels Bohr. And if you've had high school chemistry, I'm going to tell you right now, I don't go through all of the different models of the atom. But if you've had high school chemistry, kind of to go back in your brain where I am right now, there was the Bohr model of the atom, there was the Thomson model of the atom, there was the Rutherford model of the atom, there were all those different models of the atom. I'm not going through all those. I'm basically to the point of we know we have a positive nucleus, we know electrons are in the energy levels, and then it was Niels Bohr who helped us figure out these energy levels have certain amounts of energy. And he did it by observing fireworks in essence. Now, it wasn't truly fireworks that he observed, but what do we see in fireworks? We see colors. Besides the booms and the bangs, we see colors. And what actually is making that color in the firework is the same thing that you saw yesterday and the rest of us are going to see this week in lab. It's the electrons doing something that causes the color that we see when we burn certain elements. So again, going back, electrons are in their ground state. They're in their resting state, and you've got them just hanging out here. But if you excite them with fire, think about you for a minute. I would love to have this ability, but I don't. But just imagine if I had the ability to go back here and push a button and your seat started getting hot. What would some of you immediately do? Jump up. Some of you would be up just as soon as it started getting warm, you'd be up. Others of you would be sitting there going, is it getting hot here or what? So in other words, do every one of you act the same way? No, neither do electrons. All electrons don't act the same way. Sometimes those electrons jump up. So they've been given extra energy from fire or electricity. Those electrons jump to higher energy levels. But there's an old song that says, what goes up must come down. So we can't maintain that excited state. So when they fall down, well, let's think about that for just a minute. Resting state, doesn't take much energy to be close to the nucleus, does it? But if you get excited by energy, electricity, or fire, then what did I say you did? You jump out. Did it take more energy to be out here? Did you have the energy it takes to be out here? Yes. Where'd you get it? I told you, where were the two choices you could have gotten it from? Fire or electricity. So it jumped out here to higher energy levels, but it had to fall back down to the ground state. Well, then what did it have extra of? Energy. And guess what it gave that energy off as? Light. The color that you see from fireworks is due to electrons falling from their excited state back to their ground state. The best little scenario, and it's kind of cool that you all in your lifetime have this visual to imagine it with. Do you remember the light up tennis shoes? That's the best visual of it. When you're just standing here on the ground, were those shoes lit up? No. When did they light up? You jumped up and you fell back down. And did they light up then? And that's what I'm talking about. Those electrons jump to higher energy levels, and when they fall back down, they give off color. Now, what's really, really cool about this, Niels Bohr didn't know there were energy levels. I can explain it to you the way I'm explaining it to you, but what's so amazing is Niels Bohr did not know about energy levels. He knew the colors existed for different elements. Different elements will burn with different color flames. That's what this week's lab is all about. How many of you were in lab yesterday? Quite a few of you. Wow, that's a lot of you. Okay, so you saw yesterday different colors of flames. I hope you kept those chemicals clean for me by Wednesday, okay? So you saw different colors of flames, right? Different elements had different colors of flames. Those colors were due to different elements. So what Niels Bohr did is he actually looked at those. Did any of you try using the spectroscope? Did any of you actually see lines? It's very hard to see the lines. Usually when you look through it, you see a rainbow, but you don't see individual lines. You've really got to look to the side of it and through the kind of the corner of your eye to see those lines. But what those lines represent are individual wavelengths of light. So here's what I want to show you. This is what Niels Bohr saw when he looked through the spectroscope for some different elements. And these are not, let me see if I can make it. There we go. See that a little bit better. So helium, for instance, or let's start with hydrogen. Hydrogen has these 1, 2, 3, 4 lines. Do you see that? Now let's think about hydrogen for a minute. How many electrons does hydrogen have total? Come on. How many? 1. Hydrogen just has 1 electron. How in the world can it be doing all that? Are we talking about burning 1 atom? No. Are we burning a lot of atoms?
I mean, at least 2.
Well, we're burning more than 2. Think about
I'm going to say at least.
at least, absolutely, at least 2. And it's going to be a whole, why is that? He knows why it is. Anybody else know why it is? Good job. Hydrogen's diatomic. Good job, Ryan. So it's diatomic. So at least 2. But again, we're not burning just 1 molecule of hydrogen. We have to be burning a lot. So are those electrons, just like I said to you earlier, if I light you up underneath your bottom, are you going to all react the same way? No. Do all hydrogen atoms, electrons act the same way? No. So what does this mean? This means that there are 4 energy shifts. And so what Niels Bohr was able to do is he saw these lines when he looked at the colors of hydrogen, when he saw hydrogen burning or electrified with electricity. It was a blue light that he saw with his eyes. When he broke that blue light apart with that spectroscope, he saw 4 individual lines. And that made him, after he saw this again and again and again, he started realizing, wait a minute, each one of those lines is at a different energy, which means the electrons have to be doing something at different energy levels. And that's how he came up with this whole concept. So tell me though, energy-wise, I want to know energy-wise, this color down here on the far left, it's around, what is that, about 410, and I think that's nanometers, but I don't know for sure. Tell me about that. Tell me, would that be a high energy or low energy color? This one right here, the 410, would that be a high energy color or low energy color? Right here. High energy color. Would that be like hydrogen's electron jumping from first energy level to second energy level? Think about that. Think about it. No. Which of these colors would be? The red. Good job. You're thinking. Why? First energy level, jump up to second energy level, fall back down. Is that much energy to give off? No. Because are these that much difference in energy? No. What about first energy level to 7th energy level and then falling back down? Would that be more like a violet color? Good. Now you're thinking. Good. And that's how he discovered this. That's how all of this was discovered. Now, I need to go backwards for just a minute though. Some of you probably don't even understand the concept of a spectroscope. Like, where did this come from? Prism. Any of you played with a prism? Maybe you've never played with a prism. I'm hopeful at least somebody, most of you in this class have seen a rainbow. You've seen a rainbow, okay? Maybe you've actually made a rainbow in your yard in the summer when you're playing with a water hose. You ever done that? And you make the rainbow because what is that doing? So the water is diffracting light. And that's what happens when we have a rainbow. I believe in God, and I personally think it is so cool that God gives us these principles in place, and we can come back and dissect it. It's like he created nature and created it all like it is, and then we can come back and say, oh, that's how that's done. That's pretty cool. I can do a rainbow too. Why is that? Because it's basically diffracting light. What light is being diffracted is white light. Where's that light coming from when you're making a rainbow, or God's making the rainbow? Where's that light coming from? The sun. Is the sun white light? Yes. That's all this. That's where that Roy G. Biv comes from. If I were to take white sunlight outside right now, go outside and take a prism or take a water hose and diffract that light, I would get all those colors of the rainbow. What this is saying, though, is that are all those colors of the rainbow in hydrogen's light? No, that's what that's saying. What about helium's light? Are all the colors of the rainbow in helium's light? No. Guys, go back to where I already showed you. this would be what you would see if you looked at the sun. White light through the prism. That's what you see. But now we're not seeing that, because are we seeing every wavelength of light? When we look at those colors from the flame test, from the different elements, are we seeing every wavelength of light? No, because what are we seeing? We're seeing energy shifts, energy transitions. That's what we're seeing. And every one of these energy transitions refers back to an energy shift within the atom. That's where that's coming from, okay? So, just a couple more questions or comments here. I want to make a note here. And we're going to, actually, I'll tell you what, let's just start filling this in and then get to the nitty-gritty. So, ground state. Tell me what you think the ground state is. Give me some words that I've used. Ground state for an atom is what? Man, you wrote my notes. Electrons are at their lowest possible energy levels. That's when the electrons are at their lowest possible energy levels. What do we call it? Besides ground state, what did I use the phrase? Resting state. Very good. It's the resting state. Is it stable? Do you think the ground state would be stable? Yes. Absolutely. Absolutely. The ground state is very stable. It is very stable, and the ground state is what we're going to be working in. We will notate electron location for the ground state. That's what we're notating. What's the excited state? When the electrons are in higher than ground state, energy levels, due to being excited with what? Fire or electricity. Good job. Fire or electricity. Would that be stable? No, it's very unstable. Very unstable. Now, I'm going to write something kind of both places here. I'm going to go back up to this fireworks article. We didn't read the article, but I explained basically what's going on in fireworks. When electrons fall from excited state back to ground state, energy is released as color. And I'll put color in quotes there because it could be different colors. It's not necessarily one color, it depends on the fall. And I'm also going to note it again here under excited state. The fall from excited back to ground state, energy is released as color. I think it's very important for you to know that it's not the jump up that gives you the color, it's the fall. It's the falling back down that releases the color. And then what is a bright line spectrum? This picture, and I'll pull this back up again. I'm not going to have you write all this. But this picture, these are bright line spectrum. This is what we had hoped that you would see through the spectroscope. Let me ask a question real quick. In lab, did you all look at the glass tubes yesterday? You did? She set them up? Okay, good. Or he, I don't know who your lab teacher. Good, okay. Did you use the spectroscope for those? That's where you were supposed to use the spectroscope, okay? Because you cannot hardly at all do it with the flames of the flame test because they are too short-lived. But good, okay. All right, so these bright line spectrum are and I'm going to give you a scenario here. Calcium. What color do we see when calcium burns? What color do we actually see when calcium burns? Get off your phone, please. What color do we actually see when calcium burns? Anybody remember from lab? Wasn't orange, should have been red, reddish orange. Should have been, I mean, it could be a little oranges, but red. What was sodium? Huh? Lighter orangish yellow, more really, yeah. Now look at the two of these. These were similar in color, but not identical. You can definitely tell a difference in these two. But do they have the same energy shifts occurring? Our eyes are not seeing every energy shift. Our eyes, it's just like the sunlight. It's just like the sunlight. What color do we see in the sun? Well, the sun itself, if we looked at the sun, it looks orangish yellow. But I'm not talking about looking at the sun. I'm saying, what is the light color from the sun? White light. It's considered to be white light. Do we see all the colors of the rainbow? In the sunlight? In the light of the sun itself? No, we just have light. It's white light. We don't see colors when it's not like you look up at the sky and we have a rainbow beam coming down. We don't see that, do we? No. Same thing is true. When we see calcium burning in that flame test, do we see these lines? No. What do we saw? What did we see? We saw that orange-red color. Now, each of these is an energy shift. What's really cool is nobody else has that exact same fingerprint as calcium has. No other element. Have any of you ever watched any old MacGyver movies or TV shows? You might even know what I'm talking about. A couple of you have seen those old MacGyver, the old one. Okay. On old MacGyver, this is so funny, and it's such a corny show now if you watch it, but on an old MacGyver, he used this principle to identify something, which was totally, you never would do this in the real world, but he burned a substance, and being MacGyver, he had every one of the bright line spectrum memorized, of course, and so he burned an unknown substance, and guess what he used as his diffraction grating? Polarized sunglasses. Now, how many of you have a pair of polarized sunglasses, and you've noticed that rainbow out of the corner of your eyes? You know what I'm talking about, don't you? That's because those polarized sunglasses are diffraction gratings. And so MacGyver in his show, in his episode, he burned this unknown substance. He didn't know what it was. And he took his sunglasses out of their lens. He took the lenses out and he turned them and he got his bright line spectrum. Kind of theoretically correct on how it would work. A little bit off in the sense that you don't have every bright line spectrum memorized, but why would it work in theory? Because every bright line spectrum is different. So what can we use bright line spectrums for? To identify. We use them to identify. And so bright line spectrum, what are they? Bright line spectrum are obtained by passing light through a diffraction grating or prism and separating into individual wavelengths. No two spectrums are the same. They are a fingerprint. So they're a fingerprint of elements. So they are used to identify. Now, all that I've discussed today, or talked about today, is actually how we came about with the quantum theory. I can explain it backwards after we already know about it, but unbelievably, all this was observed and then the quantum theory determined. So what is the quantum theory? The quantum theory is the modern atomic theory. It's a description of an atom based upon the wave properties of electrons. It's a theory that uses numbers and letters called quantum numbers. Guys, you don't have to memorize all this. Just listen to me a minute. And those quantum numbers, which are really letters, which is why this is so confusing sometimes, those quantum numbers tell the location of the electrons in the electron cloud. Up until this point, I said electrons exist in the electron cloud. Now we're saying, where are they actually? Where are they in the electron cloud? And so there's 4 quantum numbers that we're going to deal with. There's the N quantum number, which is the energy level. It's the distance of the electron from the nucleus. Is that my scenario up here with the hula hoops? I've already said it, energy level. I've already said that. Then there's also the L quantum number, which is the shape of the electron orbital. And then these two, the M quantum number is the respect to the 3 axes in space. What are the 3 axes in space? X, Y, and Z. And then the direction of the electron's spin is the S quantum number. How many ways can things spin? How many ways can things spin? 2 ways. What are they? Clockwise and counterclockwise. We had an argument in my house one day about clockwise and counterclockwise, and it dawned on me later, nobody sees a regular clock anymore. Nobody sees a normal analog clock. We have a digital clock back here, but nobody sees an analog clock. So when I say clockwise and counterclockwise, nobody knows which direction the clock goes. And so clockwise, and I heard some students the other day say they call that right. Clockwise is right, because that's how the clock goes, is right. Counterclockwise is left, if you want to call it that. But the problem is with that concept is, well, which are we at the top or are we at the bottom of the clock? And so that's a little confusing too. And so clockwise and counterclockwise are the 2 things can spin. Now, I'm going to start here for a minute because we're not going to spend much time on here, but it makes sense. What do electrons have a charge of? What do opposites do? I ask a question. What do opposites do? Attract. What do likes do? Repel. So if electrons always exist in pairs, which they do, how can electrons always exist in pairs? They have to be doing what? I've just answered it for you. Spinning in what? The same direction? Opposite directions. Think about that for a minute. If they're spinning in the same direction, are they going to be able to exist this way? No. They're spinning in opposite directions. They're going to be spinning in opposite directions. That's how they can exist in pairs, and they do. They exist in pairs. All right, let's go now with all of these. We're going to put all this together. So energy level is N. It's the distance of the electron from the nucleus. You can have 7 energy levels. Guys, you're not going to have to memorize any of this. Just listen to me a minute. You're going to know it, but you're not going to memorize it. So you don't have to like memorize these notes here. N is 1, 2, 3, 4, 5, 6, 7. If N is 1, it's closest to the nucleus. I've already talked about this more than once. Does it have much energy? Takes hardly any energy. Why? Closest to the nucleus, what do opposites do? Attract. If N is 7, it's farthest from the nucleus. Does it take more energy to be there? Yes, because it's farther from the nucleus, the attraction is not as great. Good. How do you know what the energy level is? The energy level can be found by looking at the periods or the rows on the far left of the periodic table. Now, we've already done this on another periodic table, but you've got a clean periodic table. Label your periods on your periodic table right now. The periodic table that you have, label your periods. Label your periods. How many periods are there? I already told you how many periods are there, folks. 7. So 1, 2, 3, 4, 5, 6, 7. And if you want to make it easy on this side, do the same thing. 1, 2, 3, 4, 5, and 6, just because it doesn't finish the row, and that's okay. All right. So the question is then, the energy level, or the comment is, the energy level may be found by looking at the periods on the far left of the periodic table. The highest energy level for the element is the period or the row that the element is found in. So let me ask a question. How many energy levels does potassium have electrons in? Make it easy. 4. How many energy levels does phosphorus have electrons in? 3. How many energy levels does barium have electrons in? 6. Pretty easy right there, right? Everybody gets that, okay? So now that's energy level, distance from the nucleus, and what are they doing? What are they doing in that space? What are they doing in that space is called the orbital quantum number. So the orbital quantum number indicates the shape of the orbital the electron occupies. Basically, it is the shape of the path in which the electron is traveling. The confusing probably part of this is sometimes I'll call it subshell, sometimes I'll call it shape, sometimes I'll call it orbital. They all mean the same thing. Orbital, shape, and subshell all mean the same thing. And there are 4 different shapes or paths or orbitals that can exist. Who are they? It's written right in front of you. Who are they? S, P, D, and F. S, P, D, and F. Those are the 4 shapes or 4 paths. The shape descriptions, S is a ball. S is a ball, okay? And that one, I oftentimes will basically show you a circle, okay? But it's a ball. It's a sphere. And you also have to remember, we're dealing with this in space. Are we flat Stanleys? No. We're 3-dimensional. So we're X, Y, and Z, okay? So imagine a ball, and a ball is only going to have one position on X, Y, and Z. Can you picture with me a stick, and a stick? You with me? So are we at the center of the origin of the ball is the center of X, Y, and Z? Yes? So S can only exist in one position on X, Y, and Z. And if electrons spin only 2 ways, how many electrons can be in S? 2. Only 2. Only 2 electrons can be in S, because one will be spinning one way, the other will be spinning the other way. And that's how 2 electrons can exist in S. The next subshell is P. P is like a figure 8. P is like a figure 8, okay? What axis am I on right now? X. This would be like P along X. This would be P along Y. This would be P along who? Z. Now, if you're paying any attention to what I'm doing, how many total electrons could fit in P along X?
6.
Not P along X. 2. Have I shown both electrons right now? Am I showing both electrons right now? Now am I showing both electrons?
Yep.
Does that make sense? So 2 electrons can be in P along X, and if I could do that, P along Y and P along Z, which I can't do that, it'd be how many total? 6. Is that making sense? Now, D is a 4-leaf clover. So it's like a double figure 8. It's a 4-leaf clover. I can't show you that, okay? I don't know that one but based on what you've already learned, 2 electrons fit in S, and it had 1 position, yes? 6 total electrons fit in P, and it had 3 positions. 10 total electrons can fit in D. How many positions do you think there are? 5, good job. And F, we can't even describe. F is just crazy. F we cannot describe at all. How many electrons fit in that? 14. How many positions do you think? 7. Now, based on, I've talked to you now about how many electrons, the name of the orbital, what it looks like, but I haven't said anything about energy. But just you see it right there. But which one of those was the easiest to do? Just me doing it. Which one was easier? S, then what? P, then which one's harder? And then F, I can't even describe it, so I can't do it. So which one's going to have the highest energy? F. Which one has the lowest energy? S. Now, you and me and electrons are all the same. They're lazy. Electrons don't want to work any harder than they have to. So electrons, there's 2 avenues of energy that are affecting electrons. There's the energy for the distance from the nucleus, yes? But then there's also the energy involved in what are you doing. I ran track, believe it or not. That's so hard for me even to believe. I've done a lot of things in my life I don't remember and can't believe I did. But I ran track when I was in high school for my first 2 years. Somehow or another, back then I could actually long distance run, not long. Basically, they put me in. Even if I ended up walking at the end, I got points for the team. You know, it was one of those things. So I couldn't do hurdles, though, but I had a friend who could do hurdles. Now, let me ask you a question. Which one would take more energy, hurdles or just running? Hurdles, man. That thing's, I don't know what the heck, how they do that. I mean, I'd knock myself down every time. So now, hurdles would be like P, just running would be like S. And then I'm not even going to get into that because I can't use track examples for the rest of those. But you get my point? So we can be in the lane doing running, but that same lane could also be used for hurdles. Make sense? Now, that's what's going on inside the atom. The electrons are doing something in this space from the distance, or space from the nucleus rather. They're doing something else in this space from the nucleus. But here's what's happening. Every energy level has an S. Every energy level has an S. So you're going to have a first energy level, do an S. A second energy level, they also can do an S, but what else can they also do? A P. A third energy level, they can do an S, and a P, and a D. Now, how am I knowing this? Well, read right here. The number of possible subshells in an energy level is equal to the value of the highest energy level. For example, hydrogen is energy level 1. It can only have one subshell, S. Bromine is in energy level 3. It can have 3 different subshells, S, P, and D, and goes on from there. So how do we put all this together, and why am I not focused and saying memorize this? Because the glory is the periodic table is all laid out for you. All of it laid out. Pretty cool. How many electrons can fit in S? Read it. Right now, just read it. How many electrons can fit total in S? I'm hearing a 3. Should be 2. Everybody with me?
Oh, I thought you meant like the periodic table.
Well, how many? Oh, you're thinking sulfur.
Yeah.
How many electrons can fit in the S subshell? 2. Guess what? This is the S subshell area. How many columns are there? 2. How many electrons can fit in the subshell P? 6. Can you find 6 columns on this periodic table anywhere? Say it. Where are they? Right side. This is P. Do you see those 6 columns? 1, 2, 3, 4, 5, 6. I'm going to deal with helium in a minute. How many electrons can fit in D? 10. They're here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And how many can fit in F? 14, and guess what that is down here? 14. So you don't have to memorize how many electrons fit in each subshell. You don't even have to memorize how they fill up because the periodic table is perfectly laid out for you. So this is our S subshell, this is our P subshell, this is our D, and this is our F. The only thing I want you to do is come over here and put helium. Put helium right here. And I'll talk about why helium is here in a minute, but I want you to put helium here for now, okay? Now, using this periodic table, I also want you to finish up some other labels because there's going to be some things that are going to look a little funny, but I need you to just do it for right now and to do it for today. I want you to put 3D here, and then I want you to draw an arrow over and stop it at zinc. That's the end of 3D. If you need to put a 4P here, you may. Do the same thing here, call it 4D. Really do this, guys. If you don't, you're going to be in trouble because it's not going to make sense later. I'll tell you why it does it later. I'm pretty good about telling people why things, but right now you're just going to have to do it. I'll tell you why later, but just do it right now. 5D on lutetium, and then thallium starts 6P again. Lawrencium is 6D. And it goes on over, and there actually are more, and then that is 7P again. So instead of being 4P here, it's 3D, or I'm sorry, yes, 3D, not, instead of being 4D, it's 3D, 4D, 5D, 6D. So it's one less than what you think it would be. Now look at your numbers. Where is 30, I'm sorry, where is 56? Who is 56? Here, let me zoom in a little bit. Barium is 56. Where's 57? Down at the bottom. I want you, this is like a board game. Put a circle on barium, go to 57. Go to 57 down here. And 57, you would think, would be 6F. It's actually 4F. So label it as such. And then on 70 over here on the right-hand side, put a circle and make a note, go to 71, which is 5D. Go to 71, which is 5D. All right, 88, circle, go down to 89. This is 5F. And over here, 102, go to 103, which is 6D. Make sure you have your periodic table labeled. I'll tell you the why on Thursday. Right now, do not worry about the why. Right now, just listen to me. Okay, go back up to hydrogen. Tell me how many electrons hydrogen has? 1. What, listen to me carefully. What energy level is hydrogen's 1 electron in? Energy level, energy level, energy level, energy level, 1. Energy level. Energy level. How many are there? 7. Energy level. What subshell? S. Energy level is 1. Subshell is S. Yes or no? Okay, let me say all that in a sentence. Hydrogen has 1 electron in the first energy level, S subshell. Everybody agree? Okay. Hydrogen is next to helium. Helium has how many total electrons? 2. Helium's 2 electrons are in what energy level? 1. What subshell? S. Is the subshell full? Why? How many can fit in the S subshell? 2. Is it full? Yes. Now, if I said words all the way down to iodine, 53 electrons, iodine has 2 electrons in the first energy level S subshell. Iodine has 2 electrons in the second energy level S subshell. Iodine has 6 electrons in the second energy level P subshell. Would I be writing papers on these things? That's pretty long, right? I don't want to do that. So what do? We have what's called electron configuration notation. So electron configuration notation indicates the location of electrons with respect to the energy level and subshell. So the complete electron configuration notation for hydrogen is 1s1. Now let's show what this means. Okay, hold on one second. Let's show what this means. Hydrogen is obviously the symbol of the element, yes or no? 1, this big 1, is the energy level. The big 1 is the energy level. So make a note of this make this your legend, so in case you wonder later. This S is the subshell, and this superscript 1 is the number of electrons in that subshell. That's what that means. So the big 1 is the energy level, the S is the subshell, the superscript 1 is the number of electrons in that subshell. And how we say it is literally like I said it, 1s1. That's what we say.
I was going to say, on the homework, it didn't accept this notation. I had to type out the whole thing from start to finish.
You're ahead of yourself. Hold on, okay? Because I need to see which one you're talking about, okay? Because we are going to have to do that for long ones.
Yeah.
We are going to, okay? All right. That's hydrogen. That is hydrogen. Now, I want you to rewrite hydrogen right here. And folks, I want to warn you ahead of time, you need to write neatly. It's a big number 1 and it's a little lowercase s and it's a superscript on the s, number 1. You need to write it neatly so you can understand what you're writing. Now I want you to put helium next or underneath it. Put helium. And let's look at helium right here next to it. What energy level does helium have electrons in? 1. What subshell? How many are there? 2. So helium's electron configuration notation is 1s2. Helium's configuration is 1s2. Who's next? Well, if you have not realized this yet, this is one of the reasons I say read the periodic table, but if you haven't realized this yet, do you see, and I didn't put it on here, but 1, 2, where's 3?
Lithium.
Right there. Does the periodic table read just like a book, left, right, down, left, right, down? It does. And so that's how we're going to do electron configuration notation, is just like that. So the next element is lithium. So lithium, now, just like you climb a ladder or go downstairs, you cannot skip stairs. You have to start at the beginning. So you start up here. Lithium has a total of how many electrons? Total. 3. Where are the first 2? Remember, electrons are lazy. They're going to fill up lowest energy level. Excuse me, they're going to fill up low energy first. So where are they going to fill up first? Which S? 1s. They're going to fill up 1s first. To get here, you have to go through this space. So the electron configuration notation is going to be 1s2. That's where 2 of your electrons are. Now, where's the third electron? What energy level? 2. What subshell? S. How many are there? 1. You follow what I'm doing? Second energy level, S subshell, 1 electron. You'll get it, I promise you. Everybody gets this. That's the beauty of it. Be with me. Beryllium has how many total electrons? 4. Where are the first 2? First energy level, what subshell? S. How many are there? 2. Where are the next 2? Second energy level, what subshell? S. How many are there? 2. Now I want to show you something just with these 4 elements. The last thing you wrote, let me be quiet and let you get it written down. The last thing you wrote for hydrogen was S1. Yes or no? Look at lithium. What's the last thing you wrote for lithium? S1. What do you think the last thing you're going to write for sodium is? S1. Cesium? S1. Calcium will be what though? S2. Follow? Now, anybody having an aha moment of something else that this makes them think of? The columns, what about the columns? Say it. Well, you're ahead of me. There's something we've already talked about. I haven't talked necessarily about that. I have not talked about that in this class, but you're right, Ryan, but I haven't talked about it. Column 1's going to end in 1, column 2's going to end in 2. What else do you know about column 1 having a what? Lab. Say it. Positive 1 charge. Does column 1 all have a positive 1 charge? What's column 2 have? Ah, that's why I'm doing all this. Keep that in mind. Now keep going. I want you to write down the following on here. Boron, carbon, nitrogen, oxygen, fluorine, neon. Now boron, let's do boron. Boron is right here. I just wrote this row period, this energy level. Boron is right here. Boron has how many valence electrons? 5. Where are the first 2? Come on, where are the first 2? They have to start over here. We're reading left, right, down, left, right, down. Where are the first 2? 1s2. Guys, is everyone going to have a 1s2 after helium? You with me? Everybody past helium has a 1s2. So lithium, or boron rather, is going to be 1s2. Keep going. So here's 1s2. We have to get over here. What do you have to go through though? What energy level? 2. What subshell? What subshell? How many are here? 2. So do we write 2s2? Does everybody after beryllium have a 2s2? And then what subshell are we now in? What energy level still though? 2. So 2p what? 2p1. So 2p1. Are we getting it? Be with me. Come on. All right. Carbon. What will carbon be? Carbon's going to be 1s2. Do you see it? 1s2. Keep going. 2s2. 2p2. Yes? Right here? 2p2. Now, let me stop you for a minute. Do you remember me saying a few minutes ago you don't have to memorize S holds 2, P holds 6, D holds 10? Why? Because that's the number of columns. So are all of these going to be what? Come on, this whole column will end in what? P1. Except for helium, it's over here, okay? Now, I'm going to have you finish these, but I want to read something. I want to read the whole periodic table for you, and you do it with me, okay? You do it with me if you can. If you can't, that's okay too. But I'm going to say, and then we're going to do more of this on Thursday. We're going to really go to be done quick Thursday. You need to practice this after you leave, like today. You need to do a few. I'm going to do the whole periodic table, so listen, don't put your stuff up. Watch and listen and be engaged still. Get off your phones and pay attention. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now what do you do? 4f14, follow me? 5d10, 6p6, 7s2, 5f14, and 6d7. Now let me ask you one more question. I know I'm out of time, but I want to ask you and see if you get this. Who is 4p4? What element ends at 4p4? Tell me a symbol. Good job. Do you see that? Every one of these you should be able to say that. Guys, as soon as possible, work on this. As soon as possible, or you'll forget it before Thursday, okay? I will see you Thursday.